In this part of the program, we're going to look at a delta-delta connection. Now, this means that the primary windings of the bank are delta connected, as you've seen before, and the secondary windings are also delta connected. Delta-delta connections are represented by two delta phasor diagrams. In this example, this phasor diagram illustrates the primary connections, and this phasor diagram illustrates the secondary connections. The uppercase letters A, B, and C on the primary phasor diagram illustrate connections to the primary phase wires of a delta system. The lowercase letters A, B, and C on the secondary phasor diagram illustrate the connections to the corresponding secondary distribution lines. We'll again use this simplified diagram of a three-phase transformer bank to demonstrate how this connection is made. To make our explanation easier to follow, we've numbered the transformers and their windings 1 through 3 as before. The primary windings in this transformer bank have already been connected in a delta configuration according to the primary phasor diagram. To finish the delta-delta connection, the secondary windings must be connected in a similar relationship according to the secondary phasor diagram. Again, to simplify our explanation, we've numbered the sides of the phasor diagrams that correspond to the windings in the transformers 1, 2, and 3. And we'll begin the secondary delta connection with winding number 1. On the phasor diagram, this end of the winding is connected to the X1 bushing, and this end is connected to the X3 bushing. For the moment, we'll leave the X1 end of the secondary winding and move on to the X3 end of winding number 1. According to the phasor diagram, the end of secondary winding number 1 is connected to the end of secondary winding number 2. On the transformer bank, this connection is made by installing a jumper between the X3 bushing on transformer number 1 and the X1 bushing of transformer number 2. The phasor diagram shows us that the other end of winding number 2 is connected to one end of winding number 3. On the transformer bank, this connection is made by installing a jumper between the X3 bushing of transformer number 2 and the X1 bushing on transformer number 3. To complete the secondary delta connection, the other end of winding number 3 is connected to the end of winding number 1. In our example, this connection is made by installing a jumper between the X3 bushing of transformer number 3 and the X1 bushing of transformer number 1. When all of the connections are made, each end of a secondary winding is connected to the ends of the other secondary windings. So far, we've concentrated on just making a delta connection on the secondary side of the transformer bank. In order to connect the secondary windings to the secondary distribution lines, there are a number of things that we must consider. One of the first things to be considered is the phase relationship between the primary windings and the secondary windings. Let's return to our illustration of the three-phase bank and the phasor diagrams to see how this relationship has been established. In this example, notice that the phasor diagrams are in identical positions. That is, the uppercase letters of the primary phasor diagram, which represent connections to the phases of the primary system, correspond to the position of the lowercase letters on the secondary phasor diagram, which represent connections to the secondary distribution lines. Notice also that in making the connections, we've established a relationship between the ends of the primary windings and the ends of secondary windings. That is, the H1 end of each primary winding is in the same relative position on the primary phasor diagram as the X1 end of each secondary winding on the secondary phasor diagram. In simple terms, this means that power supplied to the H1 end of a primary winding is in a similar relationship to power supplied by the X1 end of the secondary winding. To illustrate this relationship, in this example, we'll designate the three phase wires of the primary distribution system as phase A, phase B, and phase C. These correspond to the uppercase letters on the primary phasor diagram. We'll also add three secondary distribution lines to the illustration. We'll designate these lines lowercase a, b, and c, which correspond to the connections to the secondary distribution lines on the secondary phasor diagram. To establish the relationship between the H1 and X1 ends of the primary and secondary windings, whatever phase that the H1 end is connected to should correspond to the designated secondary line that the X1 bushing is connected to. On transformer number 1, the H1 end of the primary winding is connected to A phase. Therefore, the connection between the X1 bushing of transformer number 1 and the X3 bushing of transformer number 3 is connected to secondary line A. On transformer number 2, the H1 bushing is connected to phase B. Therefore, the connection between the X1 bushing of transformer number 2 and the X3 bushing of transformer number 1 is connected to secondary line B. The same relationship is maintained for transformer number 3. The H1 bushing is connected to phase C, so the connection between the X1 bushing of transformer number 3 and the X3 bushing of transformer number 2 is connected to secondary line C. And when these connections are made, each secondary line is being energized by separate ends of two secondary windings. Secondary line A, for example, is energized by the X1 side of secondary winding number 1 and the X3 side of secondary winding number 3. Similar relationships exist for the other secondary lines. Because of the relationship we've established between the H1 end of the primary winding and the X1 end of the secondary winding in each transformer, this delta-delta connection is said to have 0 degrees of angular displacement. That is, there is no phase shift between the power supplied to the primary windings and the power supplied by the secondary windings of the three-phase bank. We can see this relationship better if we refer to the phasor diagrams. In this arrangement, there is a direct correspondence in both the position and the designation of the primary phases and the secondary lines. The H1 end of primary winding number 1 corresponds to the X1 end of secondary winding number 1. In other words, there is 0 degrees of angular displacement between the windings. The same relationship holds true for each winding in the bank. There are many ways of making a delta-delta connection. If we were to rotate the secondary phasor diagram 180 degrees, for example, we would change the angular displacement. The delta-delta connection, according to this arrangement, would produce 180 degrees of angular displacement between the primary and secondary windings. Now, in many cases, utilities have established a delta-delta connection with 0 degrees of angular displacement as the standard connection for their systems. Other companies have established a different standard, which you'll learn about later on in your training. In addition to angular displacement, another consideration of a delta-delta connection is the voltage you can expect on the secondary side of the three-phase bank. You'll notice that no connection has been made to any of the X2 bushings in this bank. This means that in this example, each secondary line is being supplied with the full rated voltage of each secondary winding. The rated output voltage of these units is 240 volts. Therefore, connections between any two of the secondary lines will supply 240 volts to a secondary load. This is sometimes referred to as a straight power bank. Its primary use is for industrial and commercial customers with large three-phase power requirements. It's possible to use a three-phase bank to supply 120 volts as well as 240 volts. In order to do this, there are a couple of things that you need to know. First, in order to supply 120 volts, a ground connection must be established. The ground connection splits one of the secondary windings into two coils. Each coil can supply 120 volts. Second, the ground connection reduces some of the efficiency of the three-phase bank. On our illustration, we'll add a grounded neutral, and we'll connect the X2 bushing of transformer number 1 to the grounded neutral. In this arrangement, when the bank is energized, connections between any two of the secondary lines will provide 240 volts to a secondary load. At the same time, connections between secondary line A and neutral or secondary line B and neutral will provide 120 volts. However, a connection between the neutral and secondary line C provides 208 volts. This odd voltage is called a power leg or a wild leg. Splitting the secondary winding on transformer number 1 effectively eliminates half of a winding on the delta connection between transformers number 1 and number 3 and produces the 208 volt power leg. Although not as efficient as a straight power bank, this type of connection allows you to provide both single-phase and three-phase power from the same bank. This is what a delta-delta connection looks like in the field. We can tell it's a delta-delta connection because each primary winding is supplied with power from two separate phases of the primary system. Likewise, each secondary line is supplied from two different secondary windings. In this example, leads from each bushing are brought down to the spool rack of the secondary bus, and the delta connection is made at the spool rack. Here's the grounded neutral wire with the lead from the X2 bushing of transformer number 1 connected. This tells us that 120/240 volts can be provided by this bank. The connections at each of the remaining spools are the delta connections to the secondary lines. Here's A, here's B, and here's C. The voltage between any two of the secondary lines is 240 volts. The voltage between line A and neutral and the voltage between line B and neutral is 120 volts. The voltage between line C and neutral, the power leg, is 208 volts. In this example, we used additive polarity transformers to build this three-phase bank. If a subtractive polarity transformer were substituted for one of the units in the bank, or if three subtractive polarity transformers were used to build the bank, a delta-delta connection with 0 degrees of angular displacement could still be made, provided that the H1-X1 relationship is maintained. The only thing that would change is the position of the secondary bushings on the transformer housing. We've covered quite a bit of information in this part of the program. We've shown you how a delta-delta connection with 0 degrees of angular displacement can be used to build a three-phase bank. Keep in mind that while the principles we've covered for making a delta-delta connection will remain the same, the way the bank is actually connected to a primary system may vary depending on your company's procedures. In the last part of this program, you saw how single-phase transformers can be connected together using a delta-delta connection to form a three-phase bank with 0 degrees of angular displacement. In this part of the program, we're going to look at a three-phase YY connection that also has 0 degrees of angular displacement. Before we do that, however, we need to look at how the coils that make up the secondary winding inside each transformer we'll be using are connected. Earlier, we indicated that when a transformer is wired conventionally, the ends of the two separate coils that make up the secondary winding are joined together in series at the X2 bushing. The other ends of the coils are connected at the X1 and the X3 bushing, respectively. For Y connections, the secondary coils are often connected together in parallel. In this case, corresponding ends of each of the two coils are connected inside the transformer at the X1 bushing. The other ends of the coils are connected together at the X2 bushing. When secondary coils are connected in parallel, the X3 bushing is not used. Companies generally tape or tag the X3 bushing in some way to alert their workers not to make any electrical connections to the X3 bushing. If a unit with 4 secondary bushings is used, the connections are made outside the transformer by jumpering together the bushings connected to the corresponding ends of the windings. The result is still the same. Only 2 connections can be made to the secondary winding. You should realize that when units whose windings are connected in parallel are used to build three-phase banks, the rated output of the bank is 208 volts. Now that you've seen how the secondary windings of Y transformers are connected, let's look at a YY connection. Here we have a simplified illustration of 3 single bushing additive polarity transformers. To make our explanation easier to follow, we've labeled the transformers and their windings 1, 2, and 3. The primary windings of each unit have already been connected to the primary distribution system using a Y connection, as we saw earlier. This primary Y phasor diagram represents that connection. This phasor diagram illustrates the Y connection we're going to make on the secondary side of the three-phase bank. Notice that the phasor diagrams that illustrate the YY connection are arranged identically. The uppercase letters on this phasor diagram refer to the primary connections and the grounded system neutral. The lowercase letters on this secondary phasor diagram illustrate the secondary connections and the grounded system neutral. Again, as an aid to explaining this connection, we've numbered the windings on the phasor diagrams that correspond to the transformers 1, 2, and 3. As you'll recall, in a Y connection, one end of each winding is connected together at the system neutral. The connection is known as a Y tie. On the secondary side of this bank, we'll use jumpers to connect the ends of the secondary windings attached to the X2 bushings together. We'll then connect this Y tie to the grounded system neutral. With this done, we now need to connect the X1 bushing of each unit to the appropriate secondary distribution line. In this example, we'll designate the primary phases on this illustration A, B, and C. We'll designate the secondary lines beneath the grounded neutral, secondary A, secondary B, and secondary C. To establish a relationship between the primary and secondary windings that has 0 degrees angular displacement, whatever primary phase the H1 end of a primary winding is connected to, the X1 end of the secondary winding should be connected to the corresponding secondary line. In this case, the H1 bushing on transformer number 1 is connected to phase A. Therefore, the X1 bushing on transformer number 1 will be connected to secondary line A. Transformer number 2 is connected on the primary side to phase B, so the secondary connection will be made to secondary line B. Finally, transformer number 3 is connected to phase C on the primary side, so the X1 bushing on the secondary side is connected to secondary line C. When this is done, there is no phase shift between the primary and secondary windings of the three-phase bank, so it has 0 degrees angular displacement. As with the delta-delta connection, a YY connection with 0 degrees angular displacement is considered by many companies to be the standard connection for their system. Connections that have 180 degrees of angular displacement are also possible. You'll learn more about these later in your training. Now that we've seen how this YY connection is made, let's look at the voltage we can expect on the secondary side of this bank. Because the secondary windings are connected in parallel, the transformers used in this bank are rated for 120/208 volts. Connections made between any of the secondary lines and the grounded neutral will supply 120 volts. Connections between any 2 secondary lines will provide 208 volts. The transformers that we've illustrated so far have had 3 secondary bushings. Let's go into the field and look at how a YY connection is made using transformers with 4 secondary bushings. Here's the three-phase bank we'll work on. We can tell this is a Y primary connection because one end of each of the primary windings has been Y-tied at the case ground and connected to the system neutral. We can also see that the other end of each primary winding is connected to a phase of the three-phase system. In preparation for connecting the secondary side of the bank, this lineman is installing jumpers to parallel the ends of the secondary coils. When properly connected, the bushings on each transformer will look like this. This connection is the X1 bushing. This connection is the X2. Notice that a ground strap has been installed between the transformer housing and the X2 bushing. The strap is used to ground the transformer housing. The X1 bushings on each transformer are tied together using a Y tie and connected to the system neutral. Leads from the X1 bushings on each unit are connected to the appropriate secondary line at the secondary bus. Here's the system neutral. Here's the connection to transformer number 1. Here's the connection to transformer number 2. And here's the connection to transformer number 3. 120 volts is supplied between connections to any secondary line and the system neutral. 208 volts is supplied by connections to any 2 of the secondary lines. As with the delta-delta connection that we saw earlier, if subtractive units are to be used in making up the three-phase bank, a YY connection with 0 degrees angular displacement can still be made, provided that the H1-X1 relationship is maintained. The only difference in connecting subtractive polarity units is the physical location of the designated secondary bushings. You should understand that your company will have specific procedures that you need to follow when connecting transformer banks to a system. While these procedures may differ slightly from the examples we've shown you, the principles for making a YY connection will remain the same. In this program, we've reviewed transformers and how they operate. We've looked at basic characteristics of Y and delta primary systems. We've seen how single-phase transformers are connected to provide single-phase service, and we've seen how single-phase transformers can be connected together using delta-delta or YY connections to provide three-phase power. The principles that we've discussed are typical of most systems. Before attempting to connect transformers to your systems, however, make sure you know and follow your company procedures and safe work practices.